All right, welcome. Today, we are diving into a classic problem, number 1.36, from I E Irodov's famous Problems in General Physics. But we're not just going to find the answer, we're going to break down the solution, step by step, and really get into the physics behind every calculation, so you walk away with a deep understanding of the concepts. Let's get right into it. Look, our goal here isn't just to circle the right answer at the end. It's really about understanding the how and the why of the solution. The idea is to build up your intuition, to give you another powerful tool for your problem-solving toolkit that you can use on all sorts of other problems. So let's dive in. Okay, first things first, we've got to break down the problem statement itself. It is absolutely critical that we get a crystal clear picture of what we're given and what we're trying to find. If we don't, we're just pushing symbols around on a page without any real purpose. So here it is, straight from the source. Let's pull out the most important pieces. First, we have this expression for tangential acceleration, W tau equals A tau. And second, we have this absolutely crucial initial condition. The particle starts from rest, or negligible velocity, right at the origin, x equals 0. Let's get this organized so we can see it all at once. Over on the left, this is what we're given. We've got our tangential acceleration, which is a product of two vectors. A, which is a constant vector that always points along the x-axis, and tau, the unit tangent vector. Now remember, tau is tangent to the path, so its direction is always changing as the particle moves. And of course, we know it starts from rest. V of 0 is 0. Our goal, on the right, is to find the speed, v, but not as a function of time, as a function of its position, x. All right, now it's time to do the translation. We're going to take all these physical ideas and words and vectors and turn them into the language of mathematics, into equations that we can actually work with and solve. Let's just do a super quick review of what tangential acceleration really is. Imagine you're driving a car. When you hit the gas or the brake, you're changing your speed. That's your tangential acceleration. When you turn the steering wheel, you're changing your direction. That's your normal acceleration. We only care about the part that changes the speed, the tangential component, which is defined as dv dt. Now, that expression in the problem A tau has a very specific and important physical meaning. It's actually a dot product. What that means is we're taking the constant vector A and we're projecting it onto the direction of the particle's motion at any given instant. So the tangential acceleration is really just the piece of A that lies along the path. So let's plug in the definitions for these vectors. The vector A is easy. It's just its magnitude, A, pointing in the x direction, which we write as AI. The unit tangent vector t is always the velocity vector v divided by its magnitude, the speed v. When we take that dot product, we're left with A times the x component of the velocity, vx, all divided by the speed v. And here we are at a classic crossroads in kinematics problems. We've managed to build an equation for dv dt, but that has time in it. The problem is asking us for v as a function of position, x. So how in the world do we get t out of the equation and get x into it? And here's our secret weapon, the chain rule from calculus. This is the perfect tool for swapping variables and derivatives. We can rewrite dv dt as dv dx times dx dt. And of course, we immediately recognize that dx dt is just the definition of the x component of velocity, vx. So there it is. That's the bridge we were looking for. All right, now for the really satisfying part, the derivation. We've built two different ways to describe the exact same physical quantity, dv by dt. So now we can set them equal and watch the magic happen. So check this out. From the physics of the problem, we found that dv dt equals ax vx over v. And from calculus, using the chain rule, we found that dv dt also equals dv dx times vx. Well, if two different things are equal to the same thing, they must be equal to each other. This is the key step that's going to let us get rid of time for good. So we set them equal, and look what happens. The v sub x term is on both sides of the equation, so we can just cancel it right out. And what we're left with is this incredibly simple, beautiful differential equation. V dv is equal to a dx. All that complexity about the curved path and the changing tangent vector, it's just vanished from our equation. Okay, so what this equation tells us is the relationship between a tiny little change in speed, dv, and a tiny little change in position, dx. To find the total relationship, we just need to add up all those tiny changes, starting from our initial condition, v is 0 when x is 0, up to some general later state, v and x. And the way we add up tiny changes in calculus is, of course, integration. And thankfully, these are very straightforward integrals. The integral of v dv is just 1/2 v squared. The integral of a dx is just ax. We apply our limits of integration from 0 up to v and x, and we end up with this beautifully simple relationship, 1/2 v squared equals a times x. And now it's just one final step of algebra to solve for v. And there it is. The velocity of the particle is the square root of 2ax. So we have an answer. But as any good physicist knows, we're not done yet. We have to stop and ask ourselves, does this result actually make physical sense? This is maybe the most important step in building confidence in your solution. So let's put our solution under the microscope. We have v equals square root of 2ax. Is this actually right? And beyond that, what is it telling us about what's physically happening to this particle as it moves? Okay, let's run through a few quick checks. First, the initial conditions. If we plug in x equals 0 into our equation, we get v equals 0. Perfect, that's exactly what the problem said. Check. Next, let's check the units, the dimensionality. The units of a times x are length per time squared times length, which gives length squared per time squared. Take the square root and you get length per time. Those are the correct units for velocity. Check. And finally, just step back and look at the form of our result before we solved for v. 1/2 v squared equals ax. That looks an awful lot like the famous kinematic equation for constant acceleration, doesn't it? That strong similarity is a really, really good sign that we're on the right track. So what's the big picture here? Yeah, we solved Irodov problem 1.36, and that's great. But the real prize, the thing you should really take away from this, is the technique. We learned how to use vector projections to understand the physics, and then we used a clever trick from calculus, the chain rule, to bridge the math and get to a solution. This method is a powerful tool you can now use to tackle all sorts of problems that involve motion on a curved path, and that is way more valuable than just the answer to one problem.